In this video, we are going to summarize the most important concept of sampling distribution. If you understand this chapter, it will be easier for you to understand confidence interval and hypothesis testing. In statistics, we deal with population, and this population consists in items. This item will be represented by points. In statistic 1, we measure only one characteristic in all of these items, and let's do a simulation. When we do a simulation in statistic, we know the true parameter. Suppose that the true mean of this characteristic is mu, and the standard deviation is sigma. If we organize all of these points or all of these items according its measurement in a number line, and in this scale we have the measurement of this characteristic, and let's assume that the distribution for individual value of this characteristic is normal, mound shape. Then when we measure this characteristic in this item, according its measurement, we are going to plot this item in this point, and so on. We can plot all of this item in this number line according to its measurement, and we obtain a distribution like this. Is a mound shaped normal distribution. The most popular measurement will be this value, which is equal to the mean. All of these items have exactly this measurement, and 3 standard deviation must reach 2 points, and within these 2 points we have 99.7% of all values. For that reason, we state that the distribution of this random variable is normally distributed. Suppose that we select one sample from this population, sample size n. Suppose that the sample size is 5, but could be any sample size. Then if we select randomly 5 items from this pile, suppose that the first selection is this, the second is this one, the third is this one, the fourth is this one, the fifth is this one. That is a random selection. When we compute the mean of all of these values, we can obtain the sample's mean, x bar 1. The mean of all of these 5 measurements will be in the middle of all of them, and this value will be close to the true parameter. In this other number line, we are going to organize all samples mean according to its corresponding measurement. For example, this value that we obtained from my first sample is a value close to the mean, then we are going to plot this value here. But we are interested in how is the distribution of all possible samples mean of all samples of the same size n. Suppose that we compute for the second sample of the same size the mean, and we obtain x sub 2, and so on. Then when we plot in this number line all of these samples, each point in this number line will represent one sample. Then when we plot all points in this number line, we are going to obtain all of this value close to the true parameter. When we finish with the last sample of the same size, we are going to obtain that distribution. Is another pile of points and is symmetric and is normally distributed because the distribution for individual value is normal, and the distribution for all samples mean will be also normally distributed. And in this simulation, we are going to notice that the center of this pie will be also the true mean of the population. 3 standard deviation to the right or to the left. We are going to reach these 2 points, between which the 2 points we have 99.7% of all samples mean. In this simulation, we are going to observe that the standard deviation of this distribution will be smaller than the standard deviation of this other distribution. If the standard deviation for individual value is sigma, the standard deviation for all of this value will be this value but smaller. How much smaller? Depends on my sample size. That will be the standard deviation of all samples mean. In this simulation, we are going to conclude that the mean of all samples mean will be the mean of the population, and the standard deviation of all samples mean is the standard deviation of the population divided by the square root of n. The bigger is my sample size, the smaller will be the standard deviation, or narrower will be the distribution of all samples mean. Remember that points in that distribution represent individual items, but points in this other distribution represent samples, size n. All points in this distribution represent samples of the same size. This relationship is very important because when we increase our sample size, then all of these samples mean will be closer to the true mean of the population. It means that we can control how close we want all of these samples mean to the true parameter, changing the sample size. For example, it is possible to select the sample size such that the standard deviation is so small that the majority of these samples mean are located close to the true mean of the population in that distribution. But a statistician also studied the cases when the population is not normal like this, but could have any other shape. This shape results when we organize all of these individual values in this number line, and we could obtain one figure like this, the mean, and we have also the standard deviation that fulfill Chebyshev's rule. The great discovery of the first statistician is that doesn't matter what is the shape of the population, when my sample size is bigger than 30, the distribution of all samples mean follow a normal distribution. That is a great discovery, and the center of the distribution will be the true parameter, the true mean of the population, and the standard deviation of this distribution will be the standard deviation of the population divided by a square root of n. That is the standard deviation of all samples mean, and this is the mean of all samples mean. That is the central limit theorem. What is the limit? The central limit theorem states when my sample size increases, this distribution becomes narrower, like this, or like this, or this. When my sample size increases, then all of these samples of the same size could get a big size like this, for example. And when all of these samples of the same size are so big, the mean of all of these samples are close to the true population parameter, the true mean of the population. And the graph could be narrow, very narrow, like this line. In this distribution, when each point represents samples very big, then the mean of all of these samples are valued very close to the true mean of the population. Then doesn't matter which sample we select from this population, the sample that we select will have a samples mean very close to the true mean of the population. In the same way that we analyze the sampling distribution of all samples mean, we can study the distribution of other statistics in those samples. For example, the standard deviation, the median, the mode, and the sample proportion. The shape of the distribution of all of these statistics computed in all of these samples could be different. In this chapter, we are going to study the sampling distribution for samples mean and sample proportion. That's it. Only two statistics. For these two statistics, when the sample size is big enough, the sampling distribution of those statistics are normal. Let's study the sampling distribution of the sample proportion. Suppose that this is a population that consists of items, and remember in statistic 1 we study only one characteristic in those items, and the random variable that we use to represent this characteristic could be quantitative variable or qualitative variable. For example, if it's a quantitative variable, could be height, weight, IQ, or qualitative variable like political affiliation, religion, culture, etc. Suppose that we gather all members of the population that fulfill one condition and this characteristic, and we count all of them, and if we want to compute the proportion of all items that fulfill that condition is given by this quotient. We count all members that fulfill this condition and divide it by the total population size. Let's do a simulation again here. Suppose that we know this population proportion and we select one sample from this this population, and let's compute the sample proportion. Then we will count in this sample all items that fulfill one condition and divide it by my sample size. That will be my sample proportion. To analyze the sampling distribution of all samples of the same size, and we compute the sample proportion for all of these possible samples of the same size, we can obtain p-hat1 for the sample, p-hat2 for the second sample, p-hat3 for the third one, and so on. If the sample size is big enough, and in this case the sample size is big enough when NPQ is bigger or equal to 10, where Q is equal 1 minus P, is the complement of P. When we study the sampling distribution for samples mean, the samples is big enough when N is equal or bigger than 30. For proportion, that is the condition. NPQ is equal or bigger than 10. In those cases, when we organize all of these samples represented by points in this number line according to its corresponding sample proportion, we obtain this pile. And in the center of this pile, we have the true proportion of the population. That is the most popular sample proportion among all of these samples. Then the mean of all samples proportion will be equal to the true proportion of the population, and the standard deviation of all sample proportion will be given by PQ divided by N. Then when my sample size is big enough, the distribution of all sample proportion follow a normal distribution, and the center of the distribution is the true population proportion, and the standard deviation is given by this formula. This condition could be written in this way: NP is bigger or equal than 15 and NQ bigger and equal than 15. But I prefer to use one inequality than two inequality to verify if my sample size is big enough. Remember, if my sample size is big enough, the sampling distribution of all sample proportion follow this mathematical model. A normal distribution, the center of the distribution is the true parameter, and the standard deviation is given by this formula. Let's do this simulation in StatCrunch. I encourage you to use applets in StatCrunch to understand the most important concept in statistics. Let's go to sampling distribution, and here let's use a population that has a bell shape, and the mean of this population is 100 and the standard deviation is 5. When we click compute, we will obtain the distribution of this population, which is bell-shaped. The mean is 100 and the standard deviation is 5. We are going to select from this population sample of size 5. When we click one time, we select one sample of size 5. We have 5 observations, and the mean of these 5 observations is given by this number. Is 103, which is close to the true mean of the population, which is 100. If we select another sample of size 5, we obtain this sample randomly. The mean of this second sample was 99.49, which is close to 100. If we select another sample of size 5, that is my selection, the mean is given by 98.8, also close to 100. If we compute the mean of 1000 samples of size 5, we obtain the following distribution. You can observe that the center of the distribution is 100.04. The center of the distribution should be the same as the center of the population, which is 100. Because we have only 1000, if we select all possible samples of 5 size, for example, if we obtain 2000 samples, we obtain that distribution, 3000 samples, this distribution, and so on. If we increase the number, we can observe that the distribution becomes normal and the center will be closer and closer to 100. What happens if we increase my sample size from 5 to 50? Then the distribution of all of these green points, which represent sample of size 50, will be closer to the center. Then the distribution will be narrower. Let's change the sample size to 50. Then when we obtain 1000 samples of size 50, let's observe what happened with the distribution. You can observe here we have 1000 samples of size 50. The distribution of all of these points are close to 100, and this is the last sample of size 50. The mean of the last sample was 99, but the mean of 1000 samples is 100.03, which is close to the true mean of the population. Here we have only 1000, that we can select 2000 samples, and we observe that the sample is closer and closer and closer to 100. If we select not 7,000 samples of size 50, but all samples of size 50 from this population, all of them, not 7,000, all of them, then the mean of all of the samples will be exactly 100, the mean of the population. We can observe that in that distribution, 99.7 or 100% of all samples are between these 2 points that are very close to 100. We can select any sample of size 50, and actually the mean compute for this sample will be a value that actually is close to the true mean of the population. We can use this value, this sample's mean, to estimate the parameter, the mean of the population.